Welcome, everyone. This is the second in the Department of Mathematics lecture series. It's all about math. My name is Kumar Murthy, and I'm the chair of the Department of Mathematics. Many of you will be familiar with the department, either because you're students taking courses in mathematics or faculty interacting through seminars and other events. But for those of you who are new to the department and perhaps even to the university, let me say that the department, together with the Fields Institute for Mathematical Sciences, has a formidable presence in research in mathematics and in related fields. And we also undertake a very large teaching mission. The department teaches about 14,000 students a year, which is a very significant proportion of the total student population at U of T. And through this series, this lecture series, it's all about math. We hope to reach out to the public, including alumni, students, faculty, and to the general public, to share with them some of the amazing intellectual treasure that is rooted in mathematics and related fields. More and more of our life is being touched by mathematical ideas and is being shaped with the help of mathematics. Whether it is the linear algebra on which Google and other search engines are built, the polynomials over finite fields that make your CDs and DVDs work, or the elliptic curves that enable secure electronic transactions, mathematics is certainly finding its way into more and more aspects of daily life. Whether we take up math as a subject of study and specialization or not, it's probably a good idea to develop some kind of appreciation of the way in which it is affecting and reshaping our world. It's all about math. This series aims to bring speakers who can shed light on the bigger perspective of what mathematics is to help us develop a broader appreciation. And today's speaker is no exception to that. John Horton Conway, born in 1937 in England, is a prolific mathematician who has made deep contributions to the theory of finite groups, knot theory, number theory, combinatorial game theory, and coding theory, to name a few. He's also well known in the field of recreational mathematics, notably the invention of the game of life. He has, I deliberately mentioned that. He has an amazing ability to express deep mathematical ideas in ordinary language that makes them accessible to everyone. Conway is currently professor of mathematics at Princeton University. Over the years, he has received many, many honors, in particular the Berwick Prize in 1971. He was elected a Fellow of the Royal Society of London in 1981 and was the first recipient of the Polya Prize in 1987. He is the subject of a recent biography, Genius at Play, by Siobhan Roberts, who's here somewhere. Yes, over there, yes. Published in Canada by Penguin Random House. And I believe Siobhan actually has a few copies of the book available. So after the lecture, you can purchase them and have John autograph them for you. So let us then sit back and prepare to enjoy a wonderful treat as John Conway speaks to us about surreal numbers.
Okay, thank you. It's a little bit hard to follow an introduction like that. So, well, just thank you. What I'm going to tell you is really, I think, the greatest surprise of my mathematical life. I'm going to tell you about it. I started off trying to understand something of the game of Go and ended up discovering the largest collection of numbers that well, inventing, somebody said, discovering more numbers than anybody else ever did, which, since that includes Cantor and Dedekind and various other people, is quite something. And I think it's deserved, actually. I mentioned I discovered them. I didn't invent them or anything. I'm firmly on the sort of Platonist side of the philosophical spectrum for mathematics. What I was trying to understand was the game of Go. Now, I never did succeed in understanding the game of Go, let me say that straight away. But I noticed one or two things about it. It's played on a huge, well, comparatively huge, 19 by 19 square, roughly. It's not actually square. The Japanese really make it deliberately just a little bit non-square, but never mind, it doesn't matter. And you place your Go counters, called stones, on intersections of this board. I'm just, one player places black stones, and this color is called black, whatever color it actually is, and the other color white. And, well, there are certain rules. It doesn't very much matter what the rules are. The rules are actually quite difficult to understand because, well, because they're difficult to understand. After a time, most of the board is filled up. I'll just sort of squiggle on it. Now, suppose we're at this situation where there are 4 empty regions, which I've labeled A, B, C, and D. Then the rules of the game force you effectively, you can only put a counter in one particular place. And that will either be in A, or in B, or in C, or in D. And your move only affects the region, only directly affects, anyway, the region that you put your counter in. If you're the white player, you put a white counter in. If you're a black player, you put the black counter in. And you leave the other ones alone. Now, that gives rise, or exemplifies, the notion of a sum of games. So let me draw you another picture, which is supposed to illustrate the sum of chess and, do you call it checkers here, or drafts, as we call it in England? Checkers, okay. So here's the board for one of these things, you know. This is the sort of checkers game. And then here's the board for the chess game, set up as they are fairly near the beginning. And I'm no good at drawing people. So I will pretend the two people have just left the room for the moment. The players are called left and right. Oh, sorry, that's the player called right. That's his chair. Oh, no, it's her chair. I have a slight convention that left is male and right is female. They're sometimes called Lefty and Rita. There's nothing prejudicial, or no statement is made of any kind by giving them sexes. It just helps with the pronouns. You say he, she, and you know which player you're talking about, rather than saying the player left and the player right, and so on. Okay. And the way you play the sum of these two games, chess and checkers, or checkers and chess, is when it's your move, you make a move that would be legal for you if that were the entire game, and you leave the other game alone. And if, then your opponent chooses, possibly independently of whatever you chose, behaves in the same way, makes a move which would be legal for her. Let me just sort of try and introduce these conventions a little bit at a time. If that were the entire game. And you might have a situation where one player makes 5 consecutive moves in the checkers game and doesn't touch the chess game at all. And then suddenly notices, oh, it developed into a rather threatening position in the chess game, I'd better make a move there. I hope you understand that the moves you make, if there's a camera just focused on one particular game, it sees a rather unusual game where the players do not move alternately. Fine. Now, what happened was I was in Cambridge University at the time, and then the British Go champion became a research student at Cambridge in the math department, and he used to bring in his Go-playing friends occasionally, and they played Go. Okay. And Cambridge being what it was, people would stand around and discuss the moves and try and work out why this one was better than that one, and so on. What it did for me was decide to study what I later called the theory of partisan sums of, or sums of partisan games, which I'd intended to study for quite some time, but never got around to it. The theory of sums of games was first developed for what are nowadays thought of as NIM-like games, independently by Peter Michael Grundy in England and Roland Sprague in Germany. And what they found out was that any impartial game, impartial is now a technical term, it means the players have the same legal moves as each other. Not very many games have that property, neither checkers nor chess does. The players have exactly the same legal moves. These two games have a rather different property, which is their moves are related by a sort of symmetry. If you turn the board around, you know, roughly speaking, you see that the black moves are really rather like the white moves. But impartial means rather more than that. It means that the black moves are exactly the same as the white moves, the black legal moves. Anyway, for impartial games, the theory says, the Sprague-Grundy theory says that every impartial game is equivalent in a certain sense to a NIM heap, and then in particular that applies to the sum of two NIM heaps. And that's that. So there is, and since NIM heaps are characterized by integers, non-negative integers to be more precise, that means there must be an addition operation on integers, which, you know, it's a kind of sum. It's not the usual sum. For instance, the sum of a NIM heap of size 3 and a NIM heap of size 5 is equivalent to a NIM heap of size 6. We say the NIM sum of 3 and 5 is 6, another kind of sum, or just 3 NIM 5 is 6. And once you know that operation on integers, and then exactly who wins a single NIM heap, you know everything. Perhaps I should say that the rule in NIM that I'm treating is the so-called normal play rule, which is that if you don't have a move, and it's your turn to move, you lose. And so who wins a single NIM heap? Oh, well, I should tell you, in NIM, it's the last player who can move that wins, because his opponent then has no moves. And until then, each player has a legal move. And for a single NIM heap, it's very easy to see who wins. It's the player about to move if that NIM heap doesn't have size 0, and it's the player not about to move if it does. Anyway, so that's enough about impartial games. That theory was discovered by these two people independently, essentially between 1930 and 1940. I'm not sure who came first. Okay. But I had wanted to generalize that theory until it discussed what I called partisan games. I originally called them unimpartial. Impartial is a bad word to use in mathematics because it suggests it means not partial. And in mathematics, there are all sorts of partial things, and it usually means a little piece of a full thing. And it doesn't mean that over here. So I decided to change the name, and I think it was Richard Guy who suggested partisan, which is really quite a nice one. So the opposite of partisan is impartial. Partisan means that the moves are allowed to depend on who's making them. Okay, well, it was the greatest surprise in my life when I started studying these games with the intention of learning about Go, and instead I discovered this enormous world of numbers, which I call surreal numbers. No, I didn't call it that. I'm trying to claim the credit. Donald Knuth wrote a little book called Surreal Numbers about the theory. And it's an excellent name because it suggests several things. The two most important things is that in some sense they are super the real numbers. The real numbers sort of writ large, you might say. That's one meaning. The other meaning is it carries a hint that they are a little bit bizarre. That meaning is also appropriate. Okay, well, that's enough introduction. I hope some of you know something about Dedekind's construction of the real numbers. It doesn't very much matter if you don't, but I'll just sketch it briefly. Dedekind takes the rational numbers as given, because they're distinctly easier to understand than the real numbers. And then he says each irrational number cuts the real line between the rational numbers that are smaller than it and the rational numbers that are greater than it. Let's take the number pi, for instance. Well, pi is greater than 3, so we put 3 on the left. Oh, and it's, of course, a stronger remark is that it's greater than 0. Oh, yes, and it's also greater than minus 73. Oh, I forgot all these fractions. It's greater than 3 1/8. That's a tighter inequality. Anyway, we put all the irrational numbers that are less than pi on the left. This is a so-called Dedekind cut. And the numbers that are the rational numbers that are greater than pi on the right. And then we've got Dedekind's way of thinking about pi. If you sort of understand the logical theory of the rational numbers, and you understand set theory, which is no mean understanding, then this gives you an understanding of the real numbers. What happens with the surreal numbers, and I didn't design it like this, I just found this to be the case, is that you do Dedekind sections right from the start. You don't start with the rational numbers. Forget the rational numbers. Okay, I hope you've obeyed that. You don't know anything about the rational numbers anymore, because, and then you just listen to me. And every number, when I say number, I mean surreal number. I didn't invent that word. I wish I had. It's a wonderful name. Every surreal number every number, let's say, is obtained by taking some previously known surreal numbers, and putting them on the left, and some other ones and putting them on the right. And then every number that you put on the left must be less than every number that you put on the right. So we'll have to learn what less than means. And then that determines a number, a new number. How can that possibly be? This guy must be talking nonsense. You see, how does the business get started? You're very quiet. Well, what happens? Oh, by the way, I should say that if you're putting the numbers A and B and C on the left, and D and E and F on the right, that's the notation I use for the resulting number. Open curly bracket, A, B, C, dot, 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 slash, down slash, vertical slash, D, E, F, dot, 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 and so on. Well, initially, remember always, we have to put some previously investigated numbers on the left and some others on the right. Initially, there aren't any previously investigated numbers. So the earliest number we build, so to speak, is this one. Nothing on the left, nothing on the right. That's the number that I call 0. That's the definition. Well, it's one definition of 0. Good. Now I've got 0. I haven't told you yet what less than means, and I'm not going to for just a moment. But it's clear already from what I have said that this is a number, because every number on the left is less than every number on the right. There aren't any numbers on the right, so I don't have to check any cases at all to check the statement I just made. So this is a number now. Oh, I'm sorry, what a pity. I wanted to put it over here. This is a number that I call 1. Every now and then I say that 1 is the simplest number greater than 0. Is equivalent, so to speak, to this notation. Now, I'm going to try your patience quite a lot in this lecture by leaving things hanging until I can later explain things. And this one is the one I call -1, which is the simplest number, less than 0. Okay, well, for the moment, let's understand that if we define a number by some particular case of this general thing, then that number will turn out to be greater than the numbers on the left and less than the numbers on the right. And then, oh yes, well, we can get going. Now you see there's a number here in which 0 and 1 are on the left. Oh, sorry. And nothing is on the right. This is the simplest number greater than 0 and 1. But if it's greater than 0 and 1, then, if all goes well, it will be, if it's greater than 1, it will be greater than 0 and 1. That sort of statement has to be proved. It's one of the irritating things I mentioned that we'll assume before it's proved. So 2 is equally the simplest number greater than 1. Okay. Numbers have lots of different definitions. That's a crucial way in which the theory I'm expounding differs from, the standard sort of theory. Over here, we have this number, the simplest number less than -1, which is also less than 0, so I could give it another name analogously to this. And this number is -2. And in fact, the whole theory is symmetric. You can sort of almost begin to guess now, I hope, what the definition of minus a number is. Here, 0 and 1 are numbers, and we will be able to prove that 0 is less than 1 when we've defined less than. And this is then a number. It turns out that a good name for it is a half. Now, this business, you can't just do what you like here, although I'm appearing to do what I like here. There are some numbers here, 0/1/2 and 1/2/1. 0/1/2 is 1/4, 1/2/1 is 3/4. You might be a little bit worried and say, where has a third gone to? Well, it hasn't been born yet. It gets born a lot later than the numbers we've just mentioned. For quite some time, they fill themselves in essentially by bisection. Okay. So after quite some time then we get a tree, an infinite tree, which looks like this. Oh, I'll go quite some distance out here. Two. Etc. You can probably appreciate already from what I've written where the general number in this lot goes to. But it doesn't stop. Over here, there's a number which is got by putting 0, 1, and 2 ... on the left and nothing on the right. That is the simplest number that's greater than all positive integers. It's actually the simplest number greater than all positive integers. I understand that the French didn't make the mistake the English made in their mathematical language. Positive, the word for positive in French, positif, includes 0. And I propose to use that word in mathematical English too. So the positive integers are the ones I've written down here. I hate saying non-negative integers. To define things by a negative property, by saying they don't have a negative property, is really awful. They have a positive property. Okay, so this number is a number that wasn't discovered by humanity for really quite a long time. It's the first of Cantor's infinite ordinal numbers, omega. Everybody else stopped counting before they got to omega. Cantor carried on. Okay. If we carry on down here, we'll get the number 0 / 1, a half, a quarter, comma, ... It turns out, when we've defined multiplication, oh my dear, I haven't defined even addition yet. Oh, well, I've got a lot to fill in. That when we've defined multiplication, it turns out that this number is the multiplicative inverse of omega. Now, Cantor never defined inverses for his ordinals. He didn't even define subtraction, unless it just happened to happen that, you know. But the first number, well, that's greater than omega is 0, 1, 2, ... omega / blank, and this is omega plus 1, and we could strike out all the finite ones now, because if you've got omega on the right, it's greater than 0, 1, 2, ... So this next number here, omega plus 1, is equally omega / blank. Oh, you can't see it. Can you tell me, can you see it now? Yeah, okay. Okay, well, you probably can't see the left-hand side of the page now, but you already know roughly what it looks like. Okay, if we alternate going right here, and then left, and then right, and then left, and then right, ooh, zumph, we get the number 0, 1 on the right. I go back and put a half on the left. I go back and put 3/4 on the right. I go back and put 5/8 on the left. I go back and put whatever number of 16ths it is, 11 16ths on the right, and so on. That number is 2/3. So 2/3 does get born in this system. It just doesn't get born at any of the finite stages. Okay? Equally, 1/3 does. Equally, pi and the square root of 2 and lots of other numbers that you know and I trust you love. But as well as those, Oh, yes, I better sort of draw the surreal line. Surreal line is a lot bigger than the real line. Here's 0, and then 1, and then these are all spaced at distance 1 from each other, and here's -1 and so on. And then here is omega. Now, omega is not the limit of these numbers. Oh, dearie no, how naive of you. Omega -1 comes before omega, and it's greater than all these finite integers as well. And so is omega -2 and so on. And not only that, how about this number, 0, 1, 2, ... omega, a half omega, oh, sorry, I didn't say that. Omega -1, omega -2, ... and that's a half of omega. And then there's a quarter omega, and an eighth of omega, and so on. And then there's this number, 0, 1, 2, ... omega, a half of omega, a quarter of omega, an eighth of omega, and so on. And guess what this is? It's a square root of omega. Now you've got your taste of what the surreal numbers are like. They form an absolutely enormous world of numbers. When I discovered them, which I remind you was an accident, I was trying to understand the game of Go, I went round in a sort of permanent daydream for about 6 weeks. Every now and then I enter that daydream again, but it usually wears off after about 5 minutes now. But initially, I felt like, who is it? Stout Quarters, in a poem by Keats, I think. You know, he walked across the continental part of America. It's really in the southern part of Latin America, I think. And he got to seeing the Pacific Ocean. And he was monarch of all he surveyed. I mean, in a certain sense, I was monarch of all I surveyed. Here was this enormous world of numbers, and nobody had ever seen it before, John, I said to myself. You know, what you're looking at now, what you're imagining, nobody else has ever seen. I fancy that Cantor had a similar feeling when he discovered the infinite ordinal numbers. Just imagine what that was like. It must have been a greater feeling, I think, than the feeling I had. And the feeling I had was pretty exhilarating, I'll tell you. But for Cantor, nobody else had ever counted beyond the infinite. Just think of that. You know, there's an amazingly large world of ordinal numbers. And here's the guy who discovered them. You know, Cantor went crazy. He was institutionalized several times during his life. He died in a lunatic asylum in Halle in 1918. It's not terribly meaningful to ask what made him crazy. The blame has sometimes been put on Kronecker. Kronecker basically thought that Cantor's work on the infinite numbers was sort of nonsense. It's not a feeling we have nowadays, but it was a legitimate feeling at the time. You know, Kronecker made this famous statement, God made the integers, all else is the work of man. And he attacked Cantor really quite viciously for his mathematical ideas. It has usually been assumed that there was anti-Semitism mixed in with that. It's interesting, and it's possible, Cantor's name, after all, is Jewish. However, it's not as obvious as all of that. Cantor's grandparents had actually converted to Christianity. And Cantor himself, one of the interesting things about it is he was very interested in scholastic exercises, the kind of stuff which we mischaracterize probably, we caricature as when we ask how many angels can dance on the head of a pin or something, or on the point of a pin maybe. You know, an intense preoccupation with infinitesimal numbers and also conversely with infinite numbers. I would feel that, well, let me say this. Cantor was quite a pugnacious person. He had a great argument with Veronese, the famous Italian, well, really the founder of the Italian school of algebraic geometry. Veronese had occasion to introduce infinitesimal numbers into his work. Essentially, no, I don't think I'll follow that up. I was going to say a few sentences about the way in which they're used in algebraic geometry. And Cantor thought, analogous to Kronecker, that Veronese's infinitesimal numbers were just nonsense. That's really because he had discovered the infinite numbers, and they were real things. You know, well, I've been speaking about his ordinal numbers, but his cardinal numbers follow on, and many people hear of the cardinal numbers before the ordinal numbers. And the cardinal numbers are the sizes of real mathematical sets. And Veronese's numbers are just formal infinitesimal numbers. And you know, we talk about abstract nonsense in mathematics and formal nonsense and so on. That's what Veronese's numbers were, and Cantor said so in no uncertain terms. Okay. So I happened to sort of, in a way, you know, Cantor is one of my really great mathematical heroes. We all ought to have Cantor as a mathematical hero. He has had more influence on the way mathematics is done than anyone else. Not only that, his influence is not just on, you know, the thing that you might know about, the creation of set theory, and we discuss everything in terms of sets nowadays. We formalize mathematics in terms of sets. But Cantor founded the Deutsche Mathematische Gesellschaft. He founded the International Mathematical Union, which conducts the international congresses. He wanted to make sure that, he socialized, unionized, perhaps I should say, mathematics. He wanted to make sure that the international congresses, particularly the first one, would be a success. It wasn't at all clear that the French would come. Cantor went and visited Poincaré, and Poincaré said effectively, well, I'll come, but I can't speak for my colleagues. I'll try to persuade them to come. And then when the Congress opened, no French delegation. That was a terrible thing. I'm tearing up now, because after a time, the French delegation marched in with Poincaré holding the flag, and about 20 people came in, and everybody burst into spontaneous ovation. Anyway, that's an aspect of Cantor's influence on mathematics that you might not have been aware of. When I speak to people normally, they don't know that. They know about his set theory. They know about all sorts of other things. So you'll have gathered that I quite admire Cantor. In 1988 or 9, I think it was, I visited Berlin for a time, And at that time, the wall was still up, the Berlin Wall. And I'm sorry, I think these stories are more interesting than the mathematics that I was going to go on. So I'll tell them. Don't worry too much. Yes, I visited Berlin. The wall hadn't yet come down. While I was in Berlin, in West Berlin, which I remind you was entirely surrounded by East Germany, and in particular East Berlin, they said to me, would you like to go and speak at Humboldt University? That was the University in East Berlin, while you're here. I think I said something about my interests in Cantor and so on. I can't remember. I certainly did later. So I said, yes, I would like to go to Humboldt. Got in one of the S-Bahn trains, so to speak, the subway system in Berlin. That was interesting, very interesting. The tracks were used by both East Berlin trains and West Berlin trains. The East Berlin trains only stopped at East Berlin stations. The West Berlin trains only stopped at West Berlin stations. I was in a train once, which was a West Berlin train, and I was going from somewhere in West Berlin to somewhere else in West Berlin, and the train suddenly stopped at an East Berlin station. And the doors, which were automatic, opened, and we froze. Because only comparatively, a few months earlier or something, somebody had tried to escape from the east, by one of these trains and been shot. So we just froze in our seats. And I should say that armed guards ran up and stood outside the train doors. Then, after a time, mercifully, the doors closed again, and we went off. There was one place where you could legally change, provided you had the right pieces of paper. And on the occasion I spoke in Humboldt University, I changed there. I've forgotten which station it was. And I had an invitation, from an official paper with various stuff stamped and signed and God knows what else. And I gave my talk in Humboldt University. And while I was there, I mentioned my interest in Cantor. And they said, oh, well, while you're here, would you like to go to Halle to see where he died? This was a sort of repetition of, while you're in West Berlin, would you like to go to Humboldt University? And now I'm in Humboldt University, would you like to go to Halle? So I said, yes, I'd quite like that. And now this was a little bit tricky. We piled into a fairly large car. From the east, of course, East Berlin, you were allowed to go into the rest of East Germany. But there was a place where, this was stopped and somebody asked us for information. I just kept very quiet, and anyway, we drove off. We got then to this former lunatic asylum, which was now some kind of warehouse or something. We peered in the windows. The windows were dusty. We saw nothing that reminded us of Cantor, except the building itself. We went and had some cafe and kuchen and some local little eating place, and then we drove back. My God, what is the time? I think I was told to aim for round about now, wasn't I? Well, I didn't aim. I was a sort of undirected missile, and I'm sorry about it, but anyway, it was interesting. The surreal numbers are absolutely fantastic things, Knuth wrote a little book about it before I did, called Surreal Numbers, and I recommend you to look at that if you want to do seriously. There was a special session of the joint meetings, most recent joint meetings, which were in Seattle, I think, and I forgot to go. Anyway, you know what the surreal numbers look like. Now, oh, I didn't tell you how to add them. I will tell you how to add them. Forgive me for telling you how to add them. It's the way you add games. Surreal numbers really are games. In a game, you have a number of left options and a number of right options. In the game a half, 0 is the left option, the only left option, and 1 is the only right option. Numbers are games. If you want to add two games, both given by definitions of this type, GL/GR, you either move in G and leave H alone. The move you make in G must be one of the left options from G, or you leave G alone and move in H. And if you're the right player, you do the same, except that you make a move legal for right. Okay? Yes, I was just wondering whether I can possibly manage to define what it means for G to be less than or equal to H. It's a little bit tedious. But all these definitions have the property that they are always the simplest thing you'd expect. You see, what do we know about G plus H? Think of numbers. But it's working for games as well. What we know about G is that it's bigger than GL and less than GR. Oh, so G plus H should be bigger than GL plus H if things are going to work the way we sort of expect them to work. And so, we know about G plus H, that it's got to be greater than these things and less than these other ones. That doesn't say it will be. When we've written down the definition of what greater than means, it turns out that that is true. The definitions are always, this is a wonderful feature about the theory, everything is the simplest thing it could possibly be. That's an absolutely wonderful thing about the theory. I found this theory in my wonder year of 1970, approximately, shortly after I found my big simple groups. It's the most astonishing thing, and I think the best thing I've ever discovered. It's absolutely wonderful. And now you can pick out the real numbers. The real numbers are those things, I'll give you the definition. They're bounded by integers. In other words, a real number is a number, that's to say a surreal number, that's between two integers. And it's equal to, G is equal to G minus 1 over n, for all n, slash G plus 1 over n. In other words, if you move it infinitesimally, you get a different number. Oh, sorry, if you move it not infinitesimally, you get a different, never mind. In my book on numbers and games, I found it a rather nice thing to do to pretend that the numbers came first. The numbers are really defined as particular games. And the definitions, which I've every now and then apologized for not giving, the definitions and the first theorems about them only take a few pages. After those few pages, you know that the surreal numbers form a field, and you have some idea how big it is. if you live with it for 10 years, you get a slightly better idea of how big it is. It's absolutely enormous. And I love the fact that I just got it by trying to understand the game of Go, by playing games, essentially. That's what I've done all my life. I've played games. And every now and then discovered something interesting as a consequence. Okay, that's it.
Well, thank you very much for those comments. True to form, Professor Conway has told us a little bit about the ideas of surreal numbers and made it look very gentle and very approachable, but hidden behind that there's quite a bit of theory and depth. I'm also happy...
I disagree with that.
You would have to, yes. Thank you also for sharing some of the personal feelings and anecdotes about Cantor and other mathematicians. That was much appreciated. We have some time for questions if somebody wants to raise a question. Yeah, Jeff?
Can you say a little more about the addition? Because you define the addition of G plus H, but then you have other additions in the definition too, so there's some more addition going on.
Yes, that's a very valuable point, really. All the definitions of this subject are inductive. And moreover, they are really transfinite inductions. Now, transfinite inductions differ from mathematical inductions with which most people are more familiar. In a mathematical induction, you start with a base case, often taken to be 1, but I prefer to take 0. So you say, the property holds of 0, and then if it holds of n, it holds of n plus 1. In transfinite inductions, it's rather different. You say, if it holds of all simpler things, then it holds of the thing you're discussing. That's the inductive hypothesis. And you don't need a base case. So let me tell you what it amounts to in the number case or the game case. If a property holds of G, provided it holds of all GL and GR, the options of G, then it holds for all G. That's the nature of induction. In set theory, that becomes the following thing, which is usually stated in a terribly stupid, opaque way. So don't read the things that tell you it in the wrong way. Just buy it from me. In set theory, the assertion is if you have a property that holds of a given set, provided only that it holds of all members of that set, then it holds of all sets. That's the axiom that should be called the axiom of set induction. And now look at it. It's very interesting. Why don't we need a base case? Let's take my definition of 0, blank slash blank, so to speak. There aren't any games simpler than 0. So whatever property you like, it holds of all games simpler than 0, there not being any. It holds vacuously. So if it's an inductive property in the sense in which I mentioned, it then holds of 0. So the case of 0 is no different to the case of omega. In the case of omega, if you have this transfinite induction property, transfinite inductive property, it reads, if a property holds of 0, 1, 2, ... then it holds of omega. Well, now you're proving the thing. Inductively, you've done cases 0, 1, 2, 3, and so on. And so case omega follows. It's a really wonderful thing. The same property that makes transfinite inductive arguments work from 0, which mathematical induction doesn't, is the same as the property that makes them capable of dealing with transfinite numbers or infinite sets. I think that's an absolutely wonderful thing. And it shouldn't be disguised the way it usually is. Yeah.
Do we have any other questions
Come on.
or comments?
Let's have a rude comment from somebody.
Could you elaborate on how the surreal numbers are related to the sum of games?
The surreal numbers are actually our games. A half is the game in which left can move to 0 and right can move to 1. In order to understand that more fully, okay, let me show you the tree of moves. Well, first of all, here is the game 0. It has an initial position, and it's illegal to make any move. Okay? Okay, here is the game 1. It has an initial position, and only the player called left can move from that position. And after left does move from that position, nobody can move, the game's over. Here is the game a half. Left can move from the initial position at the bottom, left can move to 0 and end the game. Right can move to 1, after which left can move to 0. And that ends the game. So all the things I gave as examples of numbers are really games. That was important to me. And that gives the definition of addition straight away. It also gives the definition of inequalities. Let me just say when a game is, I've defined negation. I mean, you sort of appreciate, you just make the moves legal for left that were previously legal for right, and vice versa. That's the definition of minus h, say. And now g minus h is the sum of g and minus h. Okay, that converts games into an additive group. But also, here's the definition of inequalities. G is greater than h if and only if the player left wins g minus h, no matter who starts. H is greater than g, well, you do it the other way around, if the player right wins, no matter who starts. H is equivalent to 0 if the second player wins, no matter who starts. And H is incomparable with 0. This is not a totally ordered group of games. If in the other case, which is when the first player to move wins, no matter who starts. So there are inequalities, and you'll notice that they come from games. They are natural in terms of games. The entire additive theory of numbers is the theory of games under addition. It extends to the theory of games. A game is called a number if it has a version in which all its left options, in which really you make the situation worse for yourself by making a move. In other words, all the left options of G are less than G, and all the right options of G are greater than G, if it's comparable with its left and right options. So that's what numbers are. And all those definitions are pretty natural in terms of games. When it comes to multiplication, it's not all that easy to think of. It took me about 2 years to think of the correct definition. I had what the answers were. I could tell you what the product of any two numbers was. I didn't have a good definition for it, which I found later on. So it really is true that I discovered the surreal numbers, this massive ordered field of numbers which contains the ordinals. Oh yes, it contains the ordinals. It contains the reals. You've roughly seen how. It contains Cantor's ordinal numbers, And it's a field. So it contains, things that Cantor never dreamt of, and in fact sharply disagreed with the infinitesimal things, like the inverse of omega. And it just came from games, playing games. Not really playing games, analyzing games. Analyzing children's games. Many of you will know the game called Dots and Boxes. French people call it the game of the Polytechnic in Paris because it surfaced there shortly after Napoleon sent it up. Here's what you do in Dots and Boxes. You alternately join two dots in either the horizontal or the vertical direction. These are the players moving alternately. If, however, you draw the third line of a box, your opponent can, but doesn't have to, complete that box and sign his name, X. But then he must have another go, whether he wants to or not. Okay, so he has another go, and so on. Then whoever gets most boxes wins. I'm prepared to play anybody from this audience 10 games of this tiny game of Dots and Boxes, the 4-box game, subject to the rules that you choose each time whether you want to be first or second player. And if you win any one of those 10 games, you're the winner of the tournament. Perhaps I shouldn't have said I'm prepared to play anyone. If somebody has played me before, I want them to keep their big mouths shut. Okay, come on, good enough.
So at the beginning of your lecture, you introduced the subject of surreal numbers as that you had discovered more numbers than anyone else. So
Yeah, that's not something I said, by the way. Somebody said that at the system.
that presumes that you found some way to figure out exactly how many of these there are. You found out what the cardinality of these
not
surreal numbers
really.
is.
That's an interesting question. I glided over it, which was perhaps a bit illegal of me or improper. You see, in the sense of cardinal numbers, which would be the usual way of comparing two infinite sets, this is nonsense. The collection of all surreal numbers is the same size as the set-theoretic universe in the sense of cardinal number. But there are other senses, rather analogous to measure theory, for instance, in which, the Cantor set has the same cardinal as the set of all real numbers, but it's got zero measure, it's infinitely thin. It's that kind of comparison that I was talking about in saying, making my boast, which wasn't originally my boast. When you have played with the surreal numbers, you'll appreciate what I mean. It's just mind-blowing. That's why, by the way, I often wonder whether that's what blew Cantor's mind. He didn't discover the same things, but he did the same type of thing, and his discovery was much bigger, much better. I don't mean bigger in size, really. I mean much more surprising, a much greater advance on previous things, because he seriously considered infinite collections and compared them and found there were horrendously many of them. It could have been the thing that drove him crazy. I don't say it was. Hi.
Hopefully I'll say this right. But I was wondering if you'd thought about the consequences of, instead of someone choosing one of the n games or the n domains of the Go board to make one move, if they instead made a move in each of the domains?
Yeah. Yes, I thought of all that. In my book with Bellekamp and Guy, there is a chapter called How to Play a number of games, a lot of games, in a dozen different ways. Those ways included what you just described, where you move in every component. That's called the conjunctive compound. The disjunctive compound is the one I've been discussing now, where you move in just one. The selective compound is where you move in however many you like. And then with each of those, there's a natural way of determining the ending and a slightly less natural way. Let me say what it is for the conjunctive compound. If you're playing a conjunctive compound and one of the games ends, then if you play it literally as a conjunctive compound, you can't move in that one anymore, so the whole game's over. But that seems a bit short, so to speak. So the continued compound continues on after any individual game has ended. You just play whichever games are left. So there's the continued conjunctive compound, then the shortened selective compound. The selective compound normally ends only when the whole lot of them end, but the shortened selective ends when any one of them does, and so on. This amounts to, when we take all these variations into account, that gives 12 different ways of compounding games. And for the impartial games, we give a theory for each one. That's a bit dishonest. I mean, there are one or two cases where we couldn't find the theory. I can't remember what they were.
And for these compounds, were you able to go back to thinking of them as numbers still? And
No. We think of them as what they are. That, by the way, is a thing that people often wonder, what's the appropriate kind of number for this or that or something. That's certainly not the way I think. I think, what's the answer? What's the answer to this theory? I was very, very surprised when, for the disjunctive compound, I should call it now, which is the one I've been talking about, for the disjunctive compound of partisan games, the answer turned out to be contain the theory of surreal numbers. But not all of it by any means. The theory of these games is much, much larger than the surreal numbers. But I was very, very surprised. The situation is we don't impose our own ideas on the problem of what the solution looks like. We found out, what the solution actually does look like. In the case of the selective compounds, the numbers have some relevance to it. They're not the complete answer by any means. In the case of the other compounds I was mentioning, the solutions are, they're sort of interesting, but they're sort of just combinatorially interesting, which I'm afraid I'm using, when I say just combinatorially, I'm afraid I'm using it in a pejorative sense. There's no great theory going on there. It's just the kind of thing you would expect if you tinker with this sort of stuff. The surreal numbers were just, I can't convey it. It's so big, And the games are bigger than the surreal numbers. You see, if you there's a game which I call Star, which is 0/0. Now, the additive theory and comparison and so on, all those definitions continue to work for games. Star turns out to be incomparable with 0 less than every positive number and greater than every negative number. That doesn't tell you all there is to know about it. Star plus star is 0. Star is of order 2. It's its own negative. But then there's another game, 0/star. That I called up. Up turns out to be greater than 0, but less than every positive number. And I remind you, when I say every positive number, I always mean every positive surreal number. It's less than 1 over omega. It's less than 1 over omega to the omega. It's less than... It's less than all those tiny, tiny, tiny little numbers. In fact, it's what we call a tiny game. There are much tinier games. There's a game... Up is actually tiny sub-0. There is a tiny sub-x for any x, including x being a game as well as a number. There's a game played with dominoes on a chessboard where it's played on a 2x4 rectangle of the chessboard, its value is tiny 2. Tiny 2 is terribly, terribly small. Let me just quickly say how you play domineering on a chessboard. Left puts the domino in the north-south direction, and a domino exactly covers 2 squares of the chessboard. Right puts her domino in the east-west direction. And if you can't put a domino in, because there isn't enough room when it's your turn, you lose. So you see, on a 1x1 chessboard, the value is 0, because there's not enough room for a domino. I started with 1x1 because I rather expected you'd start with 1x1. I prefer to start with 0x0, in which there's even less room for your domino. If you have a 1x2 domino, then that's worth 1 or -1, depending which way around it is. If you take an L-shaped chessboard, which are 3 squares vertical, forming the, what do I call it, the trunk of the L. Oh no, let's call it never mind. And then 2 squares across at the bottom. Let's call it a foot instead, because then we can talk about the heel and the toe and everything. That turns out to be worth a half. I mean, it's a game. It's not just worth a half. It is a half. You know, it's the game a half. Yeah. 2 copies of that L. Yes, here it is. If this is the space left on your chessboard, then it's exactly equivalent to 1. And so if we add the negative of 1, here's the negative of 1, this is a half plus a half minus 1, that's 0. I just discussed the case of 0. In the case of 0, in the earlier cases I gave, there wasn't enough room to put a domino in, and so the first player lost. That's the definition of 0. So in this game here, the first player loses. This theory is actually useful for playing childish games. And, catch me on my own and play 10 games of dots and boxes on this thing. And listen, I'll pay you to play me.
Well,
okay.
It's clear we're really getting warmed up now. And I think you'll agree with me that no matter how simply and transparently Professor Conway has presented the idea of surreal numbers, there's lots going on behind the scenes.
Yeah, there's more than meets the eye.
Yeah, certainly. So on behalf of the Department of Mathematics, let's thank Professor Conway for an excellent and stimulating talk. we have a small token of appreciation for him.
Oh my. Ooh.
And while he oohs and ahs about that, let me just remind you that he is speaking again tomorrow at 4 o'clock in the regular departmental colloquium. Please join us for that. And I also remind you that there will be copies of his book available.
Not my book.
Yes, copies of Shoban is the author, but it's a book about him, and they will be seated here, and you are welcome to get your copy and have John sign it for you. Once again, thank you for coming, and let's thank our speaker again.